All right, good afternoon, everyone. Thanks for joining this session. So my name is Laura. I'm the technical lead at RADIX.ai. And today we'd like to share our experience in building a job recommender software as a service for the Belgian Public Employment Service, who are called VDAB. And we use deep learning to solve that problem, basically. So let's dive right in. If the pointer works. No. Oh, yeah. So what will we be talking about? First, I'll just briefly introduce Radix, who we are and what do we do exactly. And then I'll tell you what our goal was at VDAB, so the Belgian Public Employment Service. And basically, the goal was to build a recommender system, as the title already indicated. So a next step in this presentation is to tell you how exactly you measure, or you can measure, the quality of a recommender system, or more generally, of a list of recommendations. I'll also motivate why we chose to use deep learning, which might not be obvious. It is, in our opinion, the right technology to solve this problem. And then finally, once we've motivated that choice, we can look at the solution architecture. How exactly does our job recommender system work? And finally, something that's not really often talked about, I think, or not often enough, is how do you actually go about deploying a machine learning solution, which is a pretty complicated task to do. So first, a bit about Radix. We'll keep it very brief. Yeah. So basically, we're a team of machine learning engineers. We've basically started in January this year, and we're growing rapidly. We see a lot of demand for machine learning-based services, and we really enjoy building machine learning-based solutions. So we work for a lot of customers, ambitious customers in the sense of their what they intend to achieve with AI. And so today will be about VDAB, but we also work, for example, for the national airport in Belgium. We use some of the latest technologies. On the top, you see some of the technologies we use to build machine learning solutions, and on the bottom, some technologies that we use to deploy more or less those solutions. So these are all part of basically this job recommender that we built for VDAB. Yeah. So we work in 3 steps. So usually we start with just a discovery phase where we talk to the customer and see what are their business problems and how could we potentially use machine learning to solve those problems. Then once we've generated a bunch of ideas, we'll try to prove that those ideas could work in a proof of concept. And if that proof is available and the customer is interested, then we can look into building an actual solution, which is what we did for VDAB and are currently doing for other customers as well. So what exactly was the goal at VDAB? Basically, whoops, I should jump back. So I just want to give a shout out to the VDAB Innovation Lab. They've been hugely supportive for us, so I want to thank them for that support. The goal at VDAB is basically a very simple REST API. In essence, the way that VDAB would consume our job recommender is with 2 endpoints. The first endpoint allows them to ask what are the best jobs for a given profile ID, and the other endpoint, which is more interesting from an employer's perspective, is what are the best profiles for a given job ID. So that's basically what VDAB wanted to consume. Of course, there are some other endpoints necessary to feed data into the system, but this is mainly how they would consume the service. So in essence, it's quite simple. How do you go about implementing something like that? Well, we looked at what data they had available, and we saw that they have these 3 chunks of data that are very useful for building such a system. The first chunk is data about the jobs. So descriptions about those jobs, the place where you would be working, the job requirements. Those are all things that go into describing jobs. And similarly, we have a bunch of documents that describe job seekers as well. And then we have something that binds these two together, which are interactions. So for example, you can imagine clicks, but it could be applications, it could be actually employers hiring candidates. So different types of interactions that tell us how interested a job seeker is in a job, or vice versa, how interested an employer with a certain job is in a job seeker. So the idea is we send all of that data into a TensorFlow model, into a deep neural net, and what we get out of that model are so-called embeddings, so job embeddings and job seeker embeddings. And these are basically numerical representations of those entities. So for example, a job would be represented by 300 numbers, and similarly, a job seeker would be represented by 300 numbers. And somehow those representations should capture the essence of what those jobs and job seekers are looking for. And we'll try to create those embeddings in a way such that their product, their inner product, or some variation of that inner product can be interpreted as some form of interest of the one entity in the other. So that's the main idea. Let's say you have access to such a system that generates these embeddings. Then the next step to implement the REST API would be this. For example, if we're interested in predicting which jobs are most interesting for a job seeker, we could simply take all of the job embeddings and list them one by one in this really long matrix. VDAB has about 200,000 active jobs at any time, so that's really a very tall matrix. And we would simply have to compute this product, this inner product that we described in the previous slide, for each of these jobs and our job seeker embedding. And that would give us a list of scores, so these green ones. And then all we'd have to do is sort those scores from beginning to end, and that would allow us to recommend, let's say, the top 10 or 20 or however many you wish, jobs to that job seeker. That's the main idea of implementing this REST API. All right, so before we continue, maybe a little bit about how you can measure the quality of such a recommender system, which may not be obvious, but that's something that you should really look into if you want to optimize for a recommender system's quality. So how does Google do it, for example, or how could Google do it? How does Airbnb do it in their bookings? Here's an example where I searched for TensorFlow Extended, which is an upcoming extension to TensorFlow. And at the time when I ran that query on Google, I saw a bunch of relevant and a bunch of irrelevant results. So I basically marked down, okay, this is a relevant result. It's really about TensorFlow Extended, the new library that I was interested in. And then the second result, for example, was about extending TensorFlow or some API, which didn't really interest me. So some of these results are relevant, some of them are irrelevant. And basically you can do that same idea, you can apply it to job recommendations as well. If you see a list of recommendations, some of those will be relevant, some of those will be irrelevant. And there are some well-known quality measures such as precision and recall that you could use to then measure the quality of such a list of recommendations. I'll briefly describe them. So precision is how many of these recommended jobs are actually relevant. So that's basically the fraction of read jobs compared to all of the recommendations. So the precision wouldn't be very high. It would be around 25–30%, let's say, in this list. And the recall is what fraction of the relevant jobs for me as a person are being recommended. So if I have 100 jobs, are all of those 100 recommended to me, or are only 10 of those recommended to me? So both of those metrics are interesting to look at. However, in practice, people will only look at a small subset of recommendations. So it makes sense to limit these measures to the top 10 results, for example. If we look at the top 10 results, the precision is quite a lot better. Now it's around 70%. 7 of these 10 recommendations are actually relevant for that user, and so we're doing pretty well. The recall is you can define in an analogous way. The problem is, though, that this precision at k measure doesn't really capture everything we want, though, because if we had the choice between these two, which both have a precision of 70%, 7 of the 10 are relevant, we'd probably choose the left one, because more of the relevant jobs are on the top of the list, and we're more likely to look at the top of the list first. So precision doesn't really capture that ranking just yet, so we still need to kind of adapt our quality measure. So instead, there's something called average precision. which basically fixes that. So I have 3 examples here of 20 recommendations, 10 of which are relevant. And in the left case, the average precision is 1. In the middle case, the average precision is 0.3. And in the last case, in the third case, it's somewhere in between. It's around 0.7. So average precision captures both the ranking and how many of these results are relevant. So that looks like a pretty good candidate for how we want to optimize our model. However, there's one big downside. None of these things that we've just discussed can be computed in practice. And the reason is that we don't actually know what irrelevant is. Users on our website, they interact with jobs, and from that you can imply or learn that they might be interested in certain jobs, but they won't typically tell you that they're not interested in certain jobs. So if a recommender system recommends a set of jobs, such as these jobs on the right, some of those recommendations will be known to be relevant, but the other recommendations, we don't know if they're relevant or irrelevant. They might be relevant, but they might not be. So it's difficult to say what it is, and therefore it's not possible to compute the average precision. So we need something else. The measure that we ended up using is called average discounted gain. So I'll spare you the mathematics behind it. Basically, the ideas are very similar to the measures that we just discussed. For those of you who are familiar with the normalized discounted cumulative gain, the average discounted gain is kind of a variant of that, which is unbiased in the situation where your feedback is implicit and only partially observed, which is exactly the situation that we're in at VDAB. So it seems like a natural fit to measure the quality of a list of recommendations. But by itself, it's not something that we can directly optimize for in TensorFlow, for example. And the reason for that is computing this number, this ADG, requires you to loop across the whole data set. So it's not something that you can train a small batch of examples on in a TensorFlow model. So you need some kind of proxy for that to use in the training phase of a neural network that kind of approximates this ADG function. And there are a couple of options there. So one option is cross entropy, which is basically one of the most popular loss functions for binary classification. So in this case, we would say if we have a pair of a job and a job seeker that we know are a match, we would want the model to predict a 1 for that match. And if we know that it's not a match, and generally, as I said, we don't have examples of non-matches or not a lot of them, so we'll pick those at random. But for those randomly combined jobs and job seekers, we'll assume that the match should be 0. So that's what we'll tell the model to achieve. We'll try to ask for, can you try to predict a 0 in case it's a random match, and can you try to predict a 1 in case we know it's a match? So that seems like a reasonable approach, except it's asking for a little bit more than we strictly speaking that we need. Cross entropy, what it's not really good at is ranking within the positive matches. It doesn't. It says that this will be a match, yes or no, but it won't rank well within the positive matches. So let's say you have 1,000 jobs that are relevant for you as a person. Those will all be predicted to have a score of 1 by the model. But how do you rank those relevant jobs for you in that case? Some of those jobs might be more relevant than others. So that's kind of where the weak point in cross entropy lies for recommender systems. So you need something else, a weaker version of cross entropy, and a good one there is called Bayesian personalized ranking, BPR. And in BPR, you ask for something a little less than in cross entropy. You're not asking for positive matches to be a 1 and unknown matches or negative matches to be a 0. You're just asking for, okay, I have this pair of a job and a job seeker that I know is a match, and I have this other pair that is I expect not to be a match. All I'm going to ask for, instead of 0s and 1s, all I'm going to ask for is that the score of the known match is higher than the score of the unknown match. That's a much weaker desire, let's say. And for that reason, the model is able to, you can kind of intuitively feel that it'll better learn how to rank individual matches, because it'll try to pull them apart. It'll know better that this is a strong match and this is maybe a weaker match. So this is the tractable proxy that we use for ADG, and is our cost function in our model. All right, so why would we even use deep learning to solve this problem? So I'll try to motivate it from 3 perspectives. Some of these you might know, but still could be interesting to see our viewpoint on it. So this is adapted from Andrew Ng. And what this graph shows you, basically on the x-axis is the amount of data that you could potentially feed into a model, and on the y-axis the performance. In our case, so I'm not talking about computational speed or anything, I'm talking about, for example, ADG or any measure of quality that you're interested in, accuracy, AUC. And what this graph tells you is that, let's look at traditional models first, so traditional machine learning models. Their performance tends to saturate as you add more data into the model. And the reason for that is that many of the traditional machine learning models have a limited parameter capacity. They just don't have enough degrees of freedom to capture all of the nuances in the data. Think about linear models, for example. They have a very small amount of parameters, which you could argue allows them to generalize better. But if you have huge amounts of data, there's just not enough degrees of freedom to learn the nuances in that data. So that's why they tend to saturate, and after a while, the gray area is really, some of those models, or many of them, may not even be computationally tractable for really large amounts of data. And training in mini batches, which is another one of deep learning strengths, allows you to train across gigabytes, hundreds of gigabytes, even terabytes of data with relatively little effort, because it's not a batch optimization. It's not a full batch optimization. So those are some of the downsides of traditional machine learning. However, you do see that they perform quite well if you have small amounts of data, because they, with their small amounts of parameters, tend to overfit less. On the neural net side, you can build larger and larger models as you increase the amount of data that you have available. So if you have a huge amount of data available, you can afford to build a really large model, and that's part of the beauty of neural networks, is that you can scale them up in terms of parameters together with the scale of your data. However, if you have less data, you can also choose to make smaller networks, so you can just scale them up and down as needed, and they would tend to perform similarly to, as traditional models if you just scale them down a little bit. So they're quite flexible in that way. And in VDAB's case, we have in the order of millions of jobs, millions of job seekers, and tens of millions of relevance labels, or these clicks that I was talking about earlier. So this really allows us to build pretty large neural networks. So what's the second motivation to use deep learning? Useful representations is another one. So in most machine learning models, the output is usually a prediction, like, is this a cat or a dog, or is this relevant, yes or no, is potentially another option. But in our case, the output of our neural network is not actually a prediction by itself. The output are useful representations of the entities that we're considering. So in our case, job seekers and jobs. We're representing them in some low-dimensional numerical space. And those representations are then used to recommend jobs to job seekers. So that's pretty unique to neural networks, that you can ask for some strange kind of output like this, as opposed to just asking for a simple prediction, yes or no, or a number, which is what most machine learning models produce. And then the third motivation for deep learning, especially in our case, is that you can, in deep learning, you can easily deal with variable length inputs. So in traditional machine learning, most of the time you have this data set and you need to reduce that to a fixed size feature space. You're forced to, because the machine learning models work that way. However, if you have a customer, where each customer has a number of purchases, for example, the number of purchases could vary per customer. So that's a variable length list of purchases per customer. One customer may have 10 purchases, the other customer may have 100. And so how do you deal with the fact that you have this variable dimension? In our case, we also have a variable dimension because the documents that are associated to the jobs and job seekers have a variable number of words. So we don't know in advance how long these documents will be. And we don't want to just arbitrarily say, okay, it's going to be 100 words. So we'd like to deal with that in a proper way and deal with these inherent variable length sequences directly. So that's also something pretty unique to deep learning. They can handle these variable length inputs. In our case, we'll take sentences or documents, represent each word with word embeddings, which are also numerical representations of these words, and then somehow summarize these lists of word embeddings into document embeddings. And those document embeddings will then somehow summarize the content of that document. So to kind of give you an idea of these word embeddings, there are some nice examples like these that show that the relations between these word embeddings kind of imply that they've somehow captured the underlying semantics. For example, you can start to do vector operations with them, like king minus queen plus man, or sorry, king minus man plus woman is ends up with queen. So you can do all kinds of interesting kind of mathematical operations with these word embeddings. And those seem to indicate that they've captured the underlying meaning. All right, so that with that out of the way, so we've kind of motivated why we're using deep learning to solve this problem. What does our solution architecture look like? Basically, at a high level of abstraction, JobNet, which is the name of, or actually internal name of the deep learning model that we built, is a cascade of useful representations. So what we do is we start with useful representations of these words, and somehow these capture the underlying semantics. And then from those, we'll build useful document representations. So jobs may consist of a number of documents. Each of those documents will try to somehow summarize based on the underlying word embeddings. And then from those document embeddings, we'll try to build job embeddings and job seeker embeddings that capture the essence of those jobs and job seekers. So we'll look at the first arrow first. How do you go from word embeddings to document embeddings? There are a couple of options. This is a popular one that I think definitely in 2017 was the de facto standard way to summarize text, summarize sentences, summarize documents. And the idea is to use so-called bidirectional LSTMs, which sounds difficult, but it's not that difficult. So what you do is you take, or you associate with each word a word embedding in your sentence or in your documents. And you initialize these LSTM cells, which are basically just simple, or you could think of as simple mathematical operations. And what they do is they just simply pass down the information from one cell to the next. So the first cell, for example, just simply receives the first word embedding and the initial state, which is, for example, an all-zero vector. It does some mathematical operation and spits out an output, which it sends to the next cell. That cell receives that output and also receives the next word embedding. It does some operation and sends that output to the next cell, and so forth. That's one of the two directions. And then in the background, there's another set of cells that processes the same sentence from backwards, from the back to the front. So that's why it's called bidirectional. And what's cool about this is that it can kind of take into account what the order is of the different words in your sentence. What's less nice about it is that it has difficulty propagating the information from the beginning of the sentence to the end of the sentence. If there's a really important word, like if, let's say, the first word was really important, the mathematical operation that happens here would need to send that information down to the next cell. This cell would have to keep that information somehow, while also receiving this input. And the following cells each would have to kind of keep propagating that information. And you can kind of see that at every step, it's like passing on a piece of paper with some message. At every step of that process, that message gets transformed a little bit, and it gets more and more difficult to propagate the information from the beginning to the end. So that's okay if you're working with sentences, but we're actually doing document embeddings. So for us, it's really challenging to propagate the information all the way from the beginning to the end. So of course we could look at sentences, but yeah. So at the end of these cells, what we do is we take the final states and we just concatenate them, or concatenate the state of the forward direction and of the backward direction, and those are just a bunch of numbers that finally represent the documents. There's another way, which I prefer myself. It's a little bit nicer to think about. It has less of the downsides of the previous approach. And this is a convolutional way to summarize a document. So here, we start with the different word embeddings, and we'll take a filter, or we'll create a filter, which is basically just an array of numbers. And we'll do something like an inner product between the word embeddings and that filter. And then what that results in is a single number. So that's this. So there's that single application of that filter on the first couple of words is a single number. And then we take that filter and we just slide it down our text, producing a whole list of numbers. And you can think of that filter basically as like a highlighter, a fluorescent marker that's going across your text, reading every word by word, and deciding whether it should output a 1 or a 0, basically. So, for example, maybe that filter, maybe that marker is looking for the level of motivation of the candidate, for example. Is this a motivated candidate? Oh yeah, this is pretty interesting. These words seem to indicate that this candidate is a motivated person. So that's maybe what the first filter, what the first fluorescent marker is looking for, and basically highlighting the different words that it thinks are relevant. But we won't just generate one filter, we'll generate hundreds of these filters. So those are the ones in gray behind. So they all generate this list of numbers that all indicate whether some aspect that filter is looking for was present in the documents. So once you have these highlighted versions of the text, the next thing to do is to summarize all these highlighted versions of the text. And you can do that simply by taking the maximum over the words dimension or over the time dimension. And what that means is just look at, was that highlighter, was that fluorescent marker, was it active at any point in the documents? Did it highlight any word at all? If it did, there's probably that probably means that property that the filter was looking for was present. And so if you have 100 filters, at the end of the day, you'll have 100 numbers, each of those looking for some particular property in that document. And that's the final state. That's the final thing that summarizes that document in a convolutional way. The nice thing about this is it doesn't suffer from the previous approach where the propagation of the information was kind of difficult. This doesn't have that. However, what it doesn't do is it won't take into account the order in which those words appear. That doesn't really matter to a degree, depending on the filter size. So if, for example, in sentiment analysis, you could imagine that the ordering of the words could be important, and so there you might choose for another technique. But this is a pretty nice way to do it as well. We ended up going with something else still, a combination of SIF and DAN. SIF is a relatively recent technique, I would say. I think it's from 2017, or it was new when we started using it anyway. Basically, SIF and DAN, I won't go into the details, but they are, let's say, computationally easier versions of the previous two ways of summarizing word embeddings. And according to the benchmarks, they perform quite well, better than LSTMs, for example, except on sentiment benchmarks, which could be for the reason that I just talked about. So SIF and DAN, look up the papers if you're interested. Definitely a nice way to summarize documents in an unsupervised way, which the previous two versions were supervised. This is an unsupervised version. So once you have these document embeddings that kind of represent the contents of those documents, you still, and in our case, they would be unsupervised up till a point. you still need to use those document embeddings to create job representations and job seeker representations. So the way that we do that is we accept different types of data from the Public Employment Service. So first of all, we have this portion here where we have, for example, for a job seeker, we'll have K documents, and each of these documents will embed using SIF, and then a number of fully connected layers to allow the different neurons to interact with each other. So these basically result in documents embeddings, one for each of the documents that belong to the job seeker. We'll also send other data, not necessarily text data, but more structured data like where the person lives in terms of geo-coordinates, the age, for example. I think, although I think we might have removed that now because of GDPR. But some of the more structured features enter in this top area here, and are also have the ability to interact with each other in fully connected layers. And then also variable length sequences don't necessarily only have to be documents. They could also be, for example, your education, which might be variable length, or your work experience might be variable length. And those things can go through a convolutional summary in the way that I described earlier. So then once each of these raw inputs have the chance to, or are somehow embedded into a new form, we concatenate all of them into one large state vector, and then allow all of those features to interact with each other. Maybe the place where the person lives somehow interacts with how that person describes himself or herself, and so forth. So that's what's happening here, and the output of that is a useful representation of that job seeker. So we don't only do that for job seekers, we also do it for jobs, of course. It's basically the same thing. It's a different pipeline. They're completely separated. So at this point in the neural network, the data just enters from the left, gets processed through all of these operations, and you end up with a bunch of numbers. And if we just run that like once from the beginning as we initialize the network, obviously these embeddings would be useless. They would just be noise. So somehow we need to be able to steer the creation of these embeddings to change the parameters of this network so that the network generates useful representations of these jobs and job seekers. And we do that by sending basically these two embeddings, which are the outputs of the network, into our Bayesian personalized ranking loss function. So that's the thing that will, when we give the network examples, we tell the network, okay, try to change your parameters such that the Bayesian personalized ranking improves just a little bit for this batch of examples. And we'll keep doing this until the network learns to create useful representations of these jobs and job seekers. Of course, you also need to feed this whole thing, and that's also something that I think is kind of glossed over a lot of times. But there's a lot of work that goes into transforming the raw data into something that is machine learning ready. It takes a lot of effort to do that. And the reason is that data, oftentimes it's part of some data warehouse, it's relational data, it's messy, it's unstructured, there could be JSONs and XMLs, there could be date fields, there could be booleans and integers and floating points, all kinds of things, all kinds of encodings and ways that people have come up with to represent these jobs and job seekers that don't necessarily match what we need for machine learning. So we need to pre-process that information so that we can actually feed it to TensorFlow. And we use Dask to do that. Dask, if you're not familiar, is something that is a useful tool that is developed by Anaconda, previously Continuum Analytics. And basically it's a task orchestration tool. It allows you to execute a graph of tasks on a single machine, across processes, on your machine, across different machines. So it's really quite powerful. And to give you an idea of this pre-processing stage, this is our task graph. So these are all the tasks that go into building this machine learning model. There's so many of them that we can't really, we could zoom in, I guess, on the individual tasks. But as you can see, it's pretty complicated. What it's useful for us is is kind of reducing this complexity. Instead of writing a whole bunch of spaghetti code, instead we have this nice graph that represents all of the things that need to happen. It allows us to debug more efficiently. In this graph, we see two main areas. The first area is something that we handle with scikit-learn. So scikit-learn, we use that to basically do all of the pre-processing. So we use machine learning to learn how to transform the original raw data into machine learning ready data. Why do I say learn? Because the way that you transform that raw data into machine learning ready data has some states associated to it. For example, if you're normalizing a numerical feature, for example, removing the mean and dividing by a standard deviation, I'm just giving an example, you need to somehow compute that mean and the standard deviation and store it somewhere. You need to store that state. That's something that you've learned. So you need to actually apply, or most of the time, you need to apply machine learning to be able to pre-process your data as part of a larger pipeline. And then once you've done that, then you can actually send it to TensorFlow. We spent so much time with Dask that we actually developed a tool called GraphChain, which made it easier and more efficient for us to work with Dask. So what is GraphChain? In one sentence, it's an efficient cache for the execution of Dask graphs. You can pip install GraphChain. It's basically a cache that you can run either locally or even on S3 wherever you like, and it'll speed up the execution of your graph, even though you might not have executed any nodes in that graph before. It'll recognize, for example, that some nodes are doing the same as others, and will save you computations there. But also, if you're rerunning tasks, it'll do only the minimal, or it'll make sure that you're only doing the minimum amount of work to get the result that you want out of the graph. And finally, so a little bit about deploying a machine learning solution. I can say that it was definitely a learning experience for us as well. We have this pipeline. What's been really good, I should say, is automating our deployments using CI/CD, so continuous integration, continuous deployments. So what that really means is just automating everything that has to do with deployment, allowing us to iterate quickly. And so what happens in practice in our setup is that when one of our developers pushes a commit to our repository, that kicks off a whole bunch of tasks. So we'll build the necessary Docker images to wrap up our application. We'll make sure that our code is healthy by linting it with all kinds of tools like Flake8 and MyPy and PyDocstyle. And then we'll also run some tests to see, okay, does it actually still work? Is nothing broken? And if all of those checks succeed, then we will go ahead and push our images to Amazon's Elastic Container Registry. So that's basically like Docker Hub, but Amazon's version of that. And then finally, we'll deploy those images to ECS, which is Amazon's container service. And that's what actually runs our application. So yeah, on the bottom you can kind of see some examples of the different steps in our deployment pipeline. Yeah, it definitely took us a while to automate this full process. There's a lot of steps that go into it. But it's not the hardest part. The hardest part for us was this. So Docker and Conda allow us to build reproducible software, but you also need reproducible infrastructure. You need to be able to set up your infrastructure in a reproducible way so that if something goes wrong, you can easily recreate it or maybe deploy it on another Amazon account or another cloud provider's account. So we had to come up with a scalable architecture. VDAB, so the Public Employment Service, serves a lot of people, and so to operate on their scale, we can't just have a single machine running somewhere. We also need the flexibility to be able to deploy without downtime. So I'm not going to go into the details, but what you can definitely tell is there are many components that go into building such an infrastructure. You need public subnets, private subnets, you need NATs and internet gateways and application load balancers. It's very complicated, and for a small company, it's a lot of work. So we had to hire some dedicated freelancers specifically for running our DevOps. Luckily, we did basically implements all of this infrastructure in a reproducible way using Terraform. Terraform is an infrastructure as code tool that allows us to describe the infrastructure that we want, and then Terraform will make sure that we get that infrastructure. It's declarative, it's like SQL. You just say what you want, and Terraform will do the rest. So that's really nice. But still, it's frustrating because maintaining such an application is still a lot of work. So what we're looking at now is, can we move from this DevOps world into a NoOps world? That's the holy grail. It's not out there yet. I don't think it's been solved yet. It's still very young. But if we can solve this, deploying machine learning solutions will be much, much easier. So if I just did a simple line count of our Terraform infrastructure declarations, and we see that we have 2,800 lines of code just to describe all of these components, which is, you really need to be an expert to understand every component of that infrastructure. So if we were to move from this more traditional setup, let's say, into functions as a service, which is what AWS Lambda offers, we would manage, let's say, an order of magnitude less infrastructure code, let's say around 100 lines. Potentially, we could use Zappa. Zappa is a deployment tool similar to Terraform. However, it's not that easy as well. I think there are a lot of challenges still left to be solved before you can go to NoOps, before you can avoid managing all of this infrastructure. And I've listed a few on this slide. Because machine learning solutions, they're not just web apps. They have all kinds of things that you need to solve. You have a training mode, you have an inference mode. The model needs to be updated regularly. New profiles, so new job seekers, new jobs may enter the system and need to be able to be served relatively quickly. So it's definitely non-trivial to fit machine learning solutions into this functions as a service kind of offering. So what are some of the challenges that we see that we're trying to solve? The first one is synchronizing states. So what does that mean, or what do I mean by that? So let's say there's a new job. That job needs to be embedded and needs to be sent, or that embedding needs to be synchronized with all of the lambdas that are actually serving the recommendations. They need access to that new embedding. So there's some synchronization issue there. And every lambda is basically stateless. So when it starts up, it doesn't know about any embeddings. So how do you solve that problem? The second issue that we're facing is cold starts. So the first time that a lambda spins up to run your function on demand, that may take a few, let's say, seconds even, and that's too slow to serve recommendations. So you need to find a way around these cold starts, and I'm sure Amazon is also working on this. But currently, if it's unacceptable for your customer that some of the requests will take longer than, let's say, a second, you need to find a way around this. And then there are all kinds of other constraints that Amazon imposes on us, such as our application size itself may be no larger than 250 megabytes, which is not allowed, especially if you're deploying TensorFlow, for example. If you look at the size of TensorFlow, it's hundreds of megabytes. So you need to strip that down to its essence just to be able to deploy it on Lambda. The same for other scientific computing libraries like NumPy and SciPy. Try fitting them on Lambda. It's really technically quite challenging. And then, of course, memory. 3 gigabytes is not a lot of memory. Depending on the cloud provider, of course, you get different amounts, but it's never, you can't ask for 60 gigabytes right now. You get a limited compute time, which is reasonable, I think, because you need to respond to the requests in a short amount of time anyway. And then you get a limited amount of scratch space, so you don't have a lot of space to write any temporary files or anything either. But definitely the last two are lesser concerns. The first ones are way more challenging. But if we can solve these, there is a way to deploy machine learning in a serverless way, in a no-ops way. So that's definitely our next challenge that we're trying to solve. So that's the end of my presentation. Thank you for your attention. And